Okay, in this video, I'm going to look at some different types of things, again, we can do with exponentials and logs. So in this first one, we're talking about earthquakes. So one of the things logs are used for is the Richter scale that you probably have heard of. So in this formula here, the Richter scale value is related to the amount of energy. And this energy in kilowatt hours, that's actually what you use for your house. That's what you run your house on. So we get this formula. It's not something you have to have memorized or anything like that, but it's just a nice little application. So in this one, it says the Richter scale, or what is the Richter scale rating if the energy released is 20,000. Okay, so I know the energy is 20,000. That tells me I'm going to substitute that in for E. So I'm going to do 0.37 times 20,000. Now, because this is all on the same side, I can type that right into my calculator. If you do not have a graphing calculator, what's nice about logs on the Richter scale is they are base 10. So this technically is the log button that is the one that's on your iPhone or just a regular normal little calculator. So the base is 10, so you don't have to do anything fancy. You can just type it all in. I got out about 4.5, so that's a 4.5 or 4.05 on the Richter scale. So probably not too big of an earthquake. Let's try one going backwards. So this one wants to know the energy if released if you knew the Richter scale was 7.6. Okay, 7.6, that's getting pretty big earthquake. So this time I know this part is 7.6. I don't know the energy part, or the E. That's what I want to solve for. Okay. So you can do a couple different ways to solve this because you could apply your properties that we've learned. I'm just going to go with getting the log by itself. So I'm going to move over that 1.46. Got to start there. Trying to get my log portion isolated. And then I'm going to divide by that 0.67. Okay, now once I get the log isolated, I'm going to rewrite it into exponential form since that's what undoes a log. Keep in mind, this one's base 10 because nothing is written. Anytime you don't see, the base written, it's base 10. So I'm going to say 10 to the power of 9.16 is equal to 0.37e. So remember, this is base, this is the answer, this over here is the power. So if you go back to rewrite it, make sure you get everything in the right spots. Again, if you use the exact numbers, that's probably the best. I'm going to kind of round them off here, though, since we're doing the, I'm typing it out. But you can use the exact answer in your calculator. This is around this number. And then we have to divide that 0.37 over, which gives me about 390659395. So we're talking hundreds, thousands, millions, billions. That's billion kilowatt hours. That's a lot of energy released by that one earthquake. Okay, another fun problem, Newton's law of cooling. This is one of the ones you can use, kind of a fun one. I went to a conference one time, and this is kind of an equation they use to tell how long a body's been dead for. So they stick that temperature probe in, and they can tell you how long it's been dead. So I put a nicer problem, though. This one's dealing with a cup of coffee. So it looks like a crazy equation, but this is your final temperature. This is your initial temperature. This is your room temperature, obviously just E. This is the rate. This is the time. And this is, again, room temperature. So in this problem, the coffee was originally 203. The room temperature is 68. And we want to figure out how long, or the cooling rate to get to 194 degrees. And the time here is just 1 minute. Okay, so the way I'm going to set that equation up, maybe I'll write it out here. So we got final temperature, initial temperature, room temperature, E, the rate, the time, and then again room temperature. So my final temperature, I want it to be 194. Okay, my initial temperature, that's I don't know why it made a circle. My initial temperature was 203 and the room temperature is 68. I don't know the cooling rate. I do know it took 1 minute, and again, the room temperature is 68. So I just substitute everything in and just do kind of your order of operations. Again, if we're doing an exponential type equation, we want to get the exponent part by itself. So I'm going to start with parentheses here, and 203 minus 68, got 135. Negative r times 1 is just negative r. I'm going to move that 68 over, so I'm going to subtract that from 196. I'm going to get 128. I'm going to divide that by the 135, get about 0.948. Again, if you want to just keep that whole number in your calculator and use it as you solve your problem, that's probably the best. This is an E problem, so the opposite of E is ln. The answer is 0.948, and the power is negative r. So if you ln that number, and again hit the answer button, I'm getting about negative 0.0532. So if I divide out the negatives, move over my decimal, I'm about 5.32% is the cooling rate for that cup. Okay, so kind of a fun application there. The last one I have is radioactive decay. That's another pretty common one. You guys that were going into nursing, I know over at the hospital they actually have a radioactive decay room for dealing with some of the drugs, maybe some of the radioactive materials that people take, as in dyes and things like that. So there's actually a room over there where they let certain items sit until the radioactive parts decay out of them. So this one's Chernobyl. I'm sure you guys have heard of that. Almost to the day. What are we at? May 1st here. And this was April 26th. What would that be? About 24 years ago or 34 years ago. So cesium was the one of the pieces of radioactive material that was left over. It has a half-life of 30.4. So what that means is, let's say you had 100 grams of cesium. In 30.4 years, it'll be down to 50 grams. So that's what half-life means. It's how long till you get half of the material. And different elements have different half-lives. So in this first one, we're just going to come up with what's the value of that constant. Okay, so if I have this equation here, I don't know how much I'm going to start with, but I do know I want to have half the amount. Oops. Okay, and I know that because I have up here the half-life is 30.4. So whatever amount I want to have half in the end. The time for that is 30.4. I don't know K. Again, those A's are going to cancel out, and I'm going to have negative 30.4 K. The opposite of an E is ln. And then I could type that in the calculator. I'm going to get about negative 0.69. And if we divide that over, K is about 0.0228. Once you get your constant, you can actually use it. So part B here, let's say we have 300 grams to start with. And we want to know how much would be left today. Well, that's 34 years have passed. So up here, 0.0228 is my constant in 34 years. If I type that in my calculator, I get about 138.18 grams, which makes sense because if I started with 300 grams, in about 30 years, it'd be 150. So we're a little past 30 years, so that answer seems reasonable. How about after 200 years? So we're going to start with 200, and we'll type in 200 years, okay? So on that one, I'm getting it down to about 3.14 grams.